Hello everyone, I'm Ramna Bansal from Indian Institute of Technology, also known as IIT Delhi. I'm going to present a part of my research entitled Conflict-Free Replicated Hypergraphs. Now, to give a brief about me, I'm a PhD research scholar in the Khosla School of Information Technology in IIT Delhi. I'm working under the guidance of Professor Sanjeeva Prasad. And prior to my PhD, I obtained MTech degree in Computer Science and Engineering from Motilal Nehru National Institute of Technology in 2010. I have also received MSc degree in Information Technology from Sam Higginbotham University of Agriculture, Technology and Sciences in 2002. Prior to this, I have received a bachelor's degree in commerce from University of Delhi in India. My research interests include databases, mHealth, and distributed systems. Talking about the paper, I'm proposing hypergraphs as a conflict-free replicated data type. Now, a very quick question is, what do you mean by hypergraph and why do we care for it? So, hypergraphs are generalized graphs where hyperedges connect more than two vertices. Since traditional data models such as relational databases, graph databases are designed and optimized in such a way that they cannot represent the richness of diversified data and complex relationships. By diversified data, we mean the data having different shapes, size, and types. And hypergraphs are important as they have such ability in hierarchical, navigational, relational, and semi-structured settings. We call a relationship complex when the relationship links and or represents multiple entities or relationships to form a higher order relation. Note that a complex relationship may describe a collection or a structure. So in this figure, we show a hypergraph that represents a biographical journal article as a complex relationship between a published paper, a list of non-duplicate authors, and a journal. A journal usually has a publisher and multiple issues. Here we represent author, publisher, reviewer, and issue date as simple entities, and article, journal, issue, and journal as relationships. We use vertices for representing entities and hyperedges for relationships. Now the question is, why do we distribute hypergraphs? To understand this, let's take a motivating scenario. So as we know that to get a paper published in a journal, three major steps are executed in sequence. So first, the paper is submitted by an author, then a set of reviewers review that paper, then at the end, the accepted paper is linked with the journal issue. Now these steps are often carried out at many different distant sites that can be spanned over a large geographical area bearing diverse network connections. And in such remote areas, we are interested in information technology, information availability along with network latencies. And replication is an approach to support information availability. But replication due to availability requires strong consistency between the replicated copies. And we know that we need consistency so that different sites of a distributed domain see the same data at the same time. But according to CAP theorem, we cannot guarantee strong consistency with information availability and network partitioning. So therefore, we require a weak consistency model, and eventual consistency is a solution. One way to achieve eventual consistency uses conflict-free replicated data types or CRDTs. In the next three slides, I'm going to briefly describe CRDTs. CRDTs address the twin requirement of availability of data and operation under network partitioning. It works with conflict-free operations with minimal synchronization overhead. It distributes replicas of mutable data using the causal consistency over a reliable delivery, and CRDTs are good in applications that have monotonically increasing record. CRDTs replicate objects by transmitting either entire state or operations. The use of these replication methods generate convergent replicated data types or CVRDTs and commutative replicated data types or CMRDTs. Further, CRDT specifications include payload and internal data structure representation and two types of operations, that is query and update. The query operations are used to investigate the locally available data objects, and the update operations change the internal state of the data objects in two phases. In the first phase, the source replica prepares parameters to be transmitted to the receiving replicas. These receiving replicas are termed as downstreams. In the later phase, downstream replicas execute the received update information asynchronously. Talking about the contribution of the paper, so in our research we leveraged the novelty of CRDT with the hypergraph semantics and structures, and as a result we provide a new CRDT that we name as HgCRDT or hypergraph as conflict free replicated data types. So the HgCRDT is designed to work on a well-formed higher order recursively defined mutable recursively defined replicable mutable hypergraphs that we discuss soon. So we present hypergraphs in HgCRDT as a collection of schematic and typed vertices and directed hyperedges. Vertices are the base cases and hyperedges connect a set of differentially linked atoms. We use the term atom to abstractly refer to these vertices and hyperedges. The vertices and hyperedges can contain a set of attributes required to build an entity or a relationship. So in this example, article is a hyperedge having paper and review as its essential attribute and journal issue and author as its referential attribute. We work with a well-founded hypergraph. We work with well-founded hypergraphs where a new hyperedge is added only when its referentially linked atoms are available in the system. For example, to build an article hyperedge, the associated author, reviewer vertices and journal issue hyperedge must exist in the system. Note that a well-founded structure brings a cyclicity, and cyclicity is an important feature in databases for several essential features such as consistency and data consistency and monotonic joins. We work with well-founded hypergraphs. We work with well-founded hyperedges that don't form any cycle and self-loop. In addition, the hyperedges are mutable in that their referentially linked atoms can be modified. Now let me explain the design of our HgCRDT. So HgCRDT involves higher order recursively defined mutable hypergraphs that are schematic and typed. The hyperedges are directed, higher ordered and mutable. And we employ operation based application in our design, and so we use CMRDT based specification that can be used in case of working with a large database, such as for a large bibliographic data set applications. We adopt the existing 2p sets of CRDTs for adding and removing vertices and hyperedges. In 2p framework, the set elements can be removed after addition but cannot be reintroduced. For our HgCRDT specification, we provide local query and update and global update operations to add, remove and modify hypergraph atoms. The communication model of HgCRDT is similar to CRDT, where operations are sent in an ordered causal fashion. The novelty of our work lies in the treatment of the well-founded recursive hypergraphical structures. Another novelty is that the set incident on a hyperedge is itself mutable 2p sets. Hyperedges involve object references to store the set rather than the complete hyperedge itself. Consequently, hyperedges are mutable as we may add and remove atoms incident on the hyperedges. The use of Thomson sets allow deletion of an atom from a set. However, since the atoms are implemented as typed objects having their implicit identity, the atoms persist across such modifications. The usage of implicit object identities explain why traditional CRDT models like key value stores and maps are not suitable for encoding hypergraphs even after some transformations. Now I'll explain a distribution scenario in the HgCRDT specification involving update operations to capture in-process article records among three distinct replicas. Note that these operations initiated at a source replica is propagated to other downstream replicas, and we introduce vertices and hyperedges in the system as per the requirement only if they don't exist. So initially at replica 1, two vertices for author A and B are added and shared with replica 2 and 3. The paper submission step involves addition of an article hyperedge at replica 1 that is also shared with others. Meanwhile, a reviewer vertex is added to the system by replica 2. However, its add information at replica 3 is delayed. But The delayed information does not affect other add operations. Thereafter, replica 2 adds and shares another reviewer vertex. Now, in case replica 2 receives a redundant add article hyperedge information, it will not affect its payload due to the use of sets. Now, going further, replica 3 adds a vertex for the publisher and 2 hyperedges for the journal and an issue. Now, adding the set of reviewers and journal issue at the respective replica requires modifying the article hyperedge. Note that the sharing of the change operation of both the replicas leads to the concurrent arrival at replica 1. This issue is resolved according to the causal order of delivery and reflects both the changes in the article. To add, we assume that a special journal issue of the same journal is introduced to the system to which article is best suited. However, the important point is the previous instance of journal issue hyperedge cannot be deleted due to its dependency on the article hyperedge. Thus, the modification of the new journal issue to the article hyperedge enables the deletion of the first one. We have implemented our HgCRDT specification as a consistency layer in our hypergraph-oriented database framework. We have used user-defined schema and underpinned an object-oriented framework in our implementation to work with typed hypergraphs. Our implementation shows an applicability of our approach in a multi-threaded environment. Currently, we involved 6 threads for this. We created a hypergraph databases to store the consistently propagating typed hypergraph objects, and this database is built atop Hypergraph DB, a general purpose data storage mechanism. So this concludes the focus of the discussion today. To end, I would like to highlight a few points. Hypergraphs can represent semi-structured hierarchical navigational complex and higher order relationships in distributed settings. We introduced a novel CRDT, that is HgCRDT, that works on a well-formed higher order recursively defined mutable hypergraphs. We proposed a detailed HgCRDT specification that uses operation-based replication using 2p2p sets. An extension of our approach introduces and implements partial replication on HgCRDT in a hypergraph-oriented database system. The future perspectives of our work includes a study of the performance of the replicated hypergraphs, particularly the scalability and complexity of our approach on large hypergraphs. A comparison of the HgCRDT specification with other CRDT based variation is also possible. At this time, I want to thank Professor Sanjeeva Prasad for his fruitful discussions and collaborative effort, Madhulika Mohanty, Himanshu Gandhi, Vijay and Geeta for their peer reviews, and the anonymous reviewers' comments. Thank you for this opportunity to present my work and for your interest and attention. If anyone has any question, suggestion or comments, I would be happy to open up the discussion on the email. My email is this, auna.bansal.iitd@gmail.com. Thank you so much.